Okay, how about if we, at this point, maybe you didn't get much down, that's fine. But hopefully at least maybe you got the format of the table in there. So how do we do this? When we're going to build a table, what's the table look like? Kind of. Okay, first thing is we want the x-axis, right? So the top of the table is just going to be, that's a little much there, I think. Yeah. Okay, so the top of the table is the x-axis, right? How many rows in the table? Two. I've got a row for x values and a row for y values, and that's it, right? Okay, so now let's talk about putting the stuff in the table that needs to be there. Let's go ahead and start with the x-intercepts. Okay? So this is where, in order to find those, we're taking our polynomial function, and this is in our textbook, and if the PDF's not on there, they'll be there today. This is a polynomial function. Sometimes people call this intercept form, and that'll make sense, or factored form. I would call it factored form, but I think our online textbook calls it intercept form. That's fine, no big deal. But there's the polynomial. To find the x-intercepts, we just want to set y, and that's y, equal to 0. So we're going to plug a 0 in for that, and let's move it to the other side. So it's on the right side of the equation, right? And we're just solving that equation. No big deal.
So all we have to do is just put a 0 on it. We don't have to worry about any.
Well, okay, I mean, kind of. But we're going to set it equal to 0, and now we're going to use the zero product property. Right now we just need to know the values of x that are going to make each of the factors 0. How many, here's my next question, how many distinct factors are there? Distinct means different. How many distinct or different factors are there with x in them? 3. Yeah, what are they? Ryan, what are they? Good. So we got the x by itself. Because that's a single, that factor's only got one term, we don't put it in parentheses normally, but we could. If we wanted to, we could put parentheses around that guy too, right? And so there are 3. Okay, by the zero product property, if we're going to try to find out when this function has a value of 0 and we solve this equation, remember what we do. The only way that that factor times that factor times that factor can be 0 is if we're multiplying by 0, right? And so that means that the factors have to have values of 0 for us to get 0 for our product. So what are the values that would make that happen? What's going to be the value of x that would make the first factor equal to 0? 0. Yeah, right? When x is 0, that factor would equal 0. And so the outcome would be 0. So there's one possibility. What's the value of x that would make that factor 0?
2.
2.
See, that makes sense.
And how about that one?
1.
Okay, so those are my x-intercepts, right? And we can really just look up there and see them. That's 0, 2, and 1. So let's put those in order. 0, 1, and 2, right? Those are my x-intercepts. So what should the corresponding y values be? 0.
Okay, why are they spread out?
Okay, questions? Here's some questions. Okay, right here. Okay, listen please. Listen. Okay,
So
baby.
why do you number them?
Why do I know? I don't number them. What I'm doing is I'm asking the question by the zero product property. And remember, this goes way back. Remember that day when I asked you guys to multiply a bunch of bizarre numbers together? And then I said times 0, which made the answer what?
0.
0. Right? Because the only way a product can equal 0 is when we multiply by 0. There's no other way. Right?
Otherwise, always would be 0.
They are, because, right? Because what are we doing? We're just taking this whole function is what gives us back y values, correct?
Yeah.
Everybody see that? Like if I were to plug in x equals 1, not 1, if I were to plug in 10, I'm going to get 10 times 8 times 9. Some big number, right? That would tell me that a point on the function was x equals 10 and y equals 10 times 8 times 9 is 720. So I get, that's my y value that goes with it,
Why
right?
can't it be 1? You said 1 and then you no 10.
Well, I didn't want to do 1 because that's going to give me a 0.
So,
But now what if I picked the values 0 or 2 or 1? If I pick 0, I'm going to get 0 times negative 2, well, 0, right? If I pick 1, I'm going to get 1 times negative 1 times 0, which is 0. If I pick 2, I'm going to get 2 times 0 times 1 is
so
0,
why you
right?
choose those numbers?
Because I want to know the places where y is equal to 0. Think about this in terms of a graph. If this is the x or the y-axis and this is the x-axis, every point that's on the x-axis has a y value of what? 0. Exactly. Does that make sense now? If we're going to look for the x-intercepts, we want to find the places where the y value that this product gives us is equal to 0, right? And so in math, that's how we communicate with the math gods. We're going to say, okay, well, we want to know where are the x-intercepts, then we're going to let this function equal 0 and use algebra to solve the equation. Yes?
So y equals 0 because there's 0 in the equation?
Y equals 0 because we're asking for the x-intercepts. Remember what we're trying to do with this function, what we're trying to do here with this table is sketch the graph, right? And so we need to find some key places on the xy plane where we know, where the function is at that time. The important places for us in Algebra 2 are going to be the x-intercepts.
So why did you choose 10?
Because I was just demonstrating that if I pick an x value, this is just to demonstrate, to remind you guys what a function does. If I pick an x value and plug it in, well, the number I get back is the y value. So if I pick 10, I'm going to get back a really big y value. Okay? I want to find the values I could pick that are going to give me 0 for y, right? We can see that 0 and 2 and 1 do that, because if I plug them in, like once again, if I pick 2, that's going to be a 2, that's going to be a 0, and that's going to be a 1. Well, 2 times 0 times 1 is 0 because the middle one equaled 0, right? So I want to find the values of x that are going to make each one of these factors equal to 0, so the product is 0, right? Make sense? We're kind of working backwards a little bit because we're just saying to ourselves, I want the function to equal 0, so I'm going to set it equal to 0, right? That gives me this equation. At that point, I've just got this equation. When I set the whole thing equal to 0, I've just got that equation. I can block out now. I can block out the f of x because I set that equal to 0, right? And put it on the other side so it looks like an equation. But now I'm just going to solve that algebraically. The work is mostly done for me though because it's already factored, right? So all I've got to do is set each factor equal to 0 to find out, by using the 0 product property, to find out what the solutions are. This would have been a much harder problem if it had been something like this. Like if I were to expand all this out, just trust me for now, I don't want to spend time talking about this. We'll get more practice with this later. If I were to expand all this out, I would get this. I would get x cubed minus 3x squared plus 2x equals 0. Okay? Later on, you guys are going to solve stuff like that. What are you going to do to solve it? You're going to factor it. You're going to turn this expression on the left side into what we're starting with here. You're going to break it into factors so that we can use the 0 product property, right? That's how we solve this, because we got to know it's really difficult to solve from right here. What do we do? There's nothing we can do. How are you going to try to somehow find the values of x just randomly that are going to make all these terms add up to 0? Impossible, right? Or highly unlikely at best. In order to solve this, you have to factor this so you make it a product of factors. So then I know that the only way that the product can be 0 is when each factor is equal to 0. So most of the hard work has already been done for you in a problem like this, right? It's given to you in a form where it's already factored, okay? Is that making sense? Okay? So then we want to we want to just find the values of x that make it equal to 0, make the y value 0, which now we can do by inspection. We can just look up here and say, oh, okay, well, 0, 2, and 1, and put those in our table, right? We know that the corresponding y values have to be 0 because we told them to be 0. We set the whole thing equal to 0, right? Okay, so we can do something now to our table. We can start to draw our table, our graph, or sketch, I should say, already. Okay, we can go down here, and here's where x is 0, so that would be, if we were to kind of try to correlate this to our sketch, that would be the y-axis, right? And then here's our x-axis, and let's see, there's 1, 2, 3, -1. Well, where were our zeros? Our x-intercepts. They were at 0, 1, and 2. So those are 3 points I know on my sketch. Okay. What's going to happen, we can kind of take our discussions from last week up a notch here. If these are x-intercepts, what has to happen between the x-intercepts?
Has to go up or down.
Has to go up or down, and it's going to have to turn around, isn't it, the function? There are going to have to be some turning points. If it goes up, it's got to turn around and come back down. So that kind of a turning point would be a maximum, right? If it goes down, then it has to turn and come back up because it's got to touch the x-axis in only those 3 places, right? See what I'm saying? So we're starting to see how the pieces of this puzzle fit together, but the key pieces are knowing where the function crosses the x-axis or touches the x-axis, right? Okay, so what else could we do? So let's go back now and let's figure out what the end behavior is, right? So we're going to do something like, let's say we want to know as x approaches positive infinity, f of x approaches what? Well, for a polynomial, isn't it? No, no, it's not. For a polynomial, the end behavior, something we always know is it's always going to be what? Well, it could be negative or positive, but it's always infinite, right? It's always going to go way up or way down, no matter what, okay? So we already know it's going to be infinite, but the question is just, what's the sign? Is it going to go up or down at the end, right? At the right end in this case. We're going to do the same thing for both endpoints. So I'll approach the left. As x approaches negative infinity, we're going to answer the question, f of x approaches what kind of infinity, positive or negative, right? So we can do this. There's a really kind of a slick little tricky way of doing this. We can just say, okay, well, let's take our function and let's just evaluate it at positive infinity and see what the sign's going to be, right? So that would look like when I want to plug a number into a function, I put it in there, right? I'm substituting it for x. So we would say this is f of positive infinity equals what? Well, how many total factors are there here, including the constant factor?
How did you do that? 3.
3. Exactly, there are 3. And how come there are 3? Okay, let's look at these. There are 3 because I have 3 factors involving x's. And is there a number other than 1 out front?
No.
There's not. What if there were a negative sign out front? Then I would have to include that. Agreed? But there's not, so I don't have to worry about it. So I've just got the signs of these 3 factors as x approaches positive infinity. Okay, so what are those signs going to be? What's the sign of infinity, of positive infinity? Positive. What's the sign of positive infinity minus 2? Now, I'm not multiplying them. If I think about this, think about positive infinity as just a huge number. Think of it as a trillion. Positive a trillion minus 2, isn't that just like pretty close to positive a trillion? So it's positive, right? You get this huge positive number, and I'm just going to subtract a wimpy little 2 from that. It's still positive, right? How about a huge positive number minus 1? Positive. So the sign of that product then is going to be what? Okay, so that's what goes there, right? So the right endpoint then, and by the way, we could even correlate this with the domain. What's the domain of any polynomial? it's well behaved, right? We know that it's just negative infinity to positive infinity every time, right? So here's our domain. We're going from negative infinity all the way out to positive infinity. The end behavior at positive infinity is positive infinity. As x approaches positive infinity, y approaches positive infinity. So what's that tell us? At the right end, it goes up. So I can put an arrow there to remind me. That's an arrow, right? Okay, what about the left? Same thing. F of negative infinity is what sign? Well, negative infinity, if I plug negative infinity in, what's the sign of negative infinity? Duh. Negative. Negative, huge number, minus 2 more is negative. Negative, huge number, minus 1 more is negative times negative is negative. And so it's negative infinity at the left endpoint. As x approaches negative infinity, y approaches negative infinity. So it's going down. Okay? That's good. That tells us a lot. Now, all we need to know is what's happening between the x-intercepts. Is it turning, is it turning around above the x-axis or turning around below the x-axis? That's it. So how would we find that? What are we going to do? Yeah, pick some test points. Some x values that are between the x-intercepts. So what's a number between 0 and 1? Yeah, 0.5 or 1/2. So let's do 1/2. And between 1 and 2? 1.5. We can write it as a decimal. That's fine. 1.5. We just need to know what the sign of the function is. Is it above or below the x-axis when it turns? So all we got to do is go back up here and try those out. We'll evaluate the function at 1/2, but all we need to know is the sign. That's it, right? So 1/2, if I plug 1/2 in for x, the first factor gives me just 1/2, positive or negative? Is 1/2 positive or negative? Positive. What about 1/2 minus 2? Positive or negative? Negative, right? Everybody agree 1/2 minus 2 is going to give me some negative number.
Yeah.
1/2 minus 1?
Positive.
Negative, isn't it? 0.5 minus 1 is going to be negative 0.5, right? And I don't care what the value is. I just want to know if I take 1/2 and I subtract a bigger number than that from it, it's going to make it negative, isn't it? Right? So positive times negative is what? Okay, so that's positive, right? And on my sketch, I know that between 0 and 1, it's going to be positive. So I'm going to have a dot above the x-axis it's got to go through, right? How about at 1.5? So 1.5, first one's just 1.5. That's positive, right? 1.5 minus 2. Positive or negative outcome? Negative is correct. 1.5 minus 1. Positive. So that's going to give me what kind of sign? Negative. Okay, so if I go down here, that means that's negative, and I'm going to get a point in between. And so now I just got to put the pieces of the puzzle together. It's pretty simple, though, from this point. What's going to happen if I start here at this point? I know I've got to touch the x-axis, but my end behavior on the right is positive. So what's the function going to do from there to the right? Yeah, it's just going up, right? Let's see, now here I've got to go up to here, so I know I'm going to cut through. What about from there on to the left? I know I've got to touch the x-axis here, but I have to go down forever. So it's just going to do that, right? Make sense? Okay, we get it? Yeah. Right? I want you to notice something here, though. I want you to make a correlation that we're going to reinforce in a second. Notice what's the power, what's the exponent of each of those factors? Are any of them being squared? They're not. They're all to the first power. When the factors are to the first power, we're going to call that a multiplicity of 1 soon. Right? That just means how many times is that factor appearing in the total function. Each of them only is to the first power. When a factor is to the first power, notice what happened at these x-intercepts. the function always cut directly through the x-axis at those x-intercepts. That's always going to happen. Okay, we're going to compare that to some other behavior in a second. But before I move on, I want to do one more thing with this. You guys had some trouble when I went back at the end of the semester and looked at where we had some issues. One of the places where we had a few issues as a group that I really need to fix is when you were solving questions like this. When you were solving questions like, for example, solving these equations. What if we had something like 2x squared minus 4x equals 0, solving quadratic equations? That is a super easy problem. But you guys were making this harder than it was. A lot of times, not everybody, but a lot of times people were saying, well, how do I plug that into the quadratic formula? Or how do I complete the square with that? Or how do I find magic numbers when it's actually so much easier than that? I'll show you why. You all now are able to tell me, and you just did, that if I look at this function right here, and I want to find the zeros, if I set it equal to 0, you can just look at that and tell me, right? The zeros are going to be at x equals 0, 2, and 1, right? Those are the x-intercepts. Those are also the solutions of this equation, right? So if we're starting off with, what if we're starting off with an equation that's harder? Like I said, what if this originally was f of x equals x cubed minus 3x squared plus 2x equals 0. We set that equal to 0 to find the intercepts. We already said that's hard to do. The only way we could do this is by factoring it, right? By breaking it into factors and using the zero product property. Then it gets really easy. Then we can just look at the factors and say, okay, 0, 2, and 1. Those are the values of x that make the factor 0. But we got to put it into that form first. This is one of the kinds of problems we're going to be doing, like in about a week, we'll be doing these. Starting with a cubic and factoring it. The first step here is dead simple though. What can we factor first? We always want to, and we talked a little bit about this. I kind of made the assumption that this was something you guys have done a lot of in Algebra 1, and I think I was wrong. I don't think maybe you did a lot of this in Algebra 1. The first thing we always want to do when we're factoring is see if we can undistribute something or factor out what's called the greatest common factor. Is there a number I can undistribute from 1 and negative 3 and 2? No, there's not. But more importantly, is there a value of x that I could undistribute? A power of x? Yeah, they each have an x in there, don't they? Right? So I should be able to factor out an x, which is the same thing as undistributing an x. Right? So my first step in solving that equation would be to say, let's undistribute an x and see what we get. Well, what's going to be left behind if we do that? What goes there is what we get when we take the first term and divide by x. Well, what's x cubed divided by x to the 1?
X squared.
X squared. Doesn't that make sense too? Because we could ask ourselves, if I undistribute an x, what would be left over? Well, x times what is x cubed? X squared, right? What's going to go here? What goes there is what we get when we take negative 3x squared divided by x to the 1. What are we going to get? What's x squared divided by x to the 1? X. X to the 2 minus 1, right? Okay, so this next one is just going to be a minus 3x, which makes sense if we ask ourselves, x times what is negative 3x squared? Well, negative 3x, right? And then the last one, what goes there is going to be this last term divided by x. Well, what's 2x divided by x? 2. Right? You get the idea? So factoring out that x is the simplest kind of factoring you could ever do. You're just undistributing it, right? But that makes life a lot easier because that tells us, when we do that, that one of the solutions is going to be x equals 0, right? Well, now I have to go further. This is harder than what we had before because now I have what's left over when I do that is quadratic. But we could do this one pretty easily. Are there magic numbers? If I try to break this apart, are there magic numbers that multiply to positive 2 and add to negative 3? What would the signs be if they multiply to a positive and add to a negative? That'd be negative, wouldn't it? Two negatives. What are they? Multiply to positive 2 and add to negative 3. Negative 2 and negative 1. And then, of course, we've still got that x out front. So look what we did. Now we've got this broken apart, and so the solutions are just 0, 2, and 1 to our equation, right? So when you see something like this, or when you did see something like this in Module 3, how should we do this? Is there a number I could undistribute here? What? What's the biggest number that divides into both 2 and 4? 2, right? So I could factor out a 2. I could even, if I want to, because this is an equation and 2 is just a constant, I can always divide both sides of an equation by any number, right? I can't divide both sides by a variable. That's a no-no, but I could divide both sides by 2 instead of even factoring it out. And what would I get? 2 divided by 2 is, so I'm going to get x squared. 4 divided by 2 is, yeah, I'll get my negative 2, right? So I could just get that if I divide both sides by 2. I don't even have to factor that part out. But then I get this equation. Bailey, can I undistribute anything from that one? I'm looking at the variables. That's what I really care about, are the variables. What do you think? Could I undistribute, Austin? You got an idea? Could I undistribute something there? An x, exactly. They each have an x, so I could undistribute an x and factor out an x, and what am I left with if I do that? X times what is x squared? X. X times what is negative 2x? Negative 2. Well, so what are my solutions? This is easy. I don't have to do, that's the easiest kind of quadratic equation to solve. What's that solution going to be? 0. When x is 0, then that makes that factor 0. Whenever I get that x by itself, the solution is always going to be x equals 0, right? What about this one? Manuel, what's going to be the solution to that one?
Negative 2.
Almost. But negative 2 minus 2 wouldn't be 0. Right? Because that's what I'm doing. I'm trying to find, I got to make this product 0 now, right? So that's when x is 0. What value of x makes that factor 0? 2. So those are my solutions, 0 and 2. Right? You get the idea? Okay? All right. How about this one? Let's go through this one together. How are we doing with time here? Oh, we can do it. We can do it. We can make it. Here we go. I need your attention. You guys just kind of follow along. You don't even have to write this down, but just follow along. Okay, so I need to know something here. If I set this equal to 0, first thing we got to do here is, what are going to be the x-intercepts? What are the zeros of this function? What values of x would make each factor 0? That one is 0 when x equals this one.
-1.
Negative 6. So my answers are negative 6, negative 1, positive 5, right?
We have 4 minutes.
We can do it.
I know, that's a lot of fun.
Take that stuff back out.
Okay, have a look, hang on, have a look. So we got to find the signs of these. What I want to know right away is, are there any of these 3 factors whose signs are never going to change and you know what it is all the time? One of these is a gimme. You don't even have to think about it. No? The one that's squared. Could any number that's squared ever be negative? No, it couldn't, right? So one thing we could do, because this one is being squared, I know that the sign of that factor is always going to be positive. Could never be negative, right? Make sense? The other 2 we'd have to check, though. When I put in positive infinity, that one's positive and that one's positive, and so I get an answer of positive infinity, right? So my right-hand behavior is going to be positive infinity. If I plug in negative infinity. I'll make this one red because I know it's always positive. It's being squared. This one's negative and that one's negative. Well, that still gives me positive, doesn't it? Right? So then out here at the left, I still get positive infinity. So it's up on both ends, right? Let's check some test points. If I check test point at, how about at -3? Let's just try this. At -3, I'm going to get what? -3 minus 5 is what? Negative or positive?
Negative.
Negative. This one's being squared, so it's always positive. -3 plus 6 is? So the overall sign is negative, right? Okay, how about at 0? That one's positive. 0 minus 5 is? Negative. 0 plus 6 is? So that's negative also. So we got everything we need. We can do our sketch. So we get zeros at -6, -1, +5. We get negative values for our test points, so they're below at both ends. How's this going to work? If I want to go up at the right end, don't I have to just do that? Okay, if I'm going up at this end, don't I just have to do that? What does this one have to do?
Down.
It's got to just graze, doesn't it? Because it can only touch right there. Okay, I want you to notice something. What do you notice about that factor? This was the one that had -1 as a solution. It was this one. Notice that this is the one that's being squared, right? I want you to see this, see that you can really draw an important parallel here. So the ones that are not being squared, once again, those were x-intercepts where the function just cut right through, right? But where it was being squared, it looked like a parabola. Okay, it just touched the x-axis. Okay? All right, we're done.